No? Okay. So then we go to our second speaker, Mr. Andrew Luong, who's going to give a lecture about the project in Chongqing in China with interesting features about the structural design. Please welcome Mr. Andrew Luong.
Good afternoon. My name is Andrew Luong, and thank you all for coming to this lecture. I know it's the last day in the conference, and it's also in the afternoon after lunch, so please bear with me. I hope there's I'll have some interesting stories and interesting design facts to share. So this is a tower that we've designed, and it's currently under construction, and we're still following with the construction. The tower is called Chongqing International Trade and Commerce Center. It's one of a number of towers that we're doing currently carrying out design for in China. An introduction to the project. The client is Chongqing Shuyan 10D Property Development, and the architect is KPF. There's also architects involved with the project, Palmer & Turner and Benoit. And the engineering is done by Arup in a total engineering manner. So we're doing the structures, MEP design, fire, acoustics, sustainability, and there's even a rail component to it because there's a railway line station that's actually cutting through our site, and we learned about that actually quite late in this design. So that's actually worked out well because the development's in phases, and I'll show you that in a little bit later. So the project's in Chongqing, and for those of you who are not familiar with China, Chongqing is actually on the Yangtze River, or the Yangtze River, by the side of the Yangtze River. The site, so the site is in actually, the river there is actually the Jilin River, which is a tributary of the Yangtze. And so outside is a very prime site. You can see the development's a very big development. It's about 690,000 square meters. And typical of this type of development in China, it's mixed use. So we get office, retail, hotel. And so the site is very large, and you can see that there's a number of towers. Tower 1 is actually under construction. It's almost finished now. Tower 1 is 250 meters tall. Tower 2 is the one I'm going to talk about, and that's the tower, if you know the towers in Hong Kong, IFC and ICC, our tower is actually taller than IFC, but shorter than ICC. So it's in that kind of range of height. And Tower 3 is a smaller tower, which is 150 meters high. This is a rendering from KPF of the three towers. And the tower shapes actually come about from the architectural symbolism of sailing ships or junks on the river. So these Chinese sailing boats, and that's where there's this curved shape which KPF has really nicely introduced into the design, and we've been able to deliver in the engineering of it to really reflect this. The tower, you can see the tower to the top floor is 440 meters high, and then to the top of the tower is 468. Now, it's a very slender tower. The aspect ratio is about 8.4. And another, I suppose, less non-typical shape of this tower is that it's oval in plan. Now, we don't see a lot of oval, oblong shaped floor plans. Usually they're rectangular or square to that nature. And that had its design challenges, but also, we managed to deliver quite an efficient structure. So I was just mentioning about the shape. So you can see on the plan, the floor plan, we have an oval shape and an elliptical shape. And there's actually these on plan, there's actually these cuts on the corners. And what they do is to reflect the architectural feature. And this also created an issue with the structure. In a couple of slides, I'll explain the structural system. But part of the concept working through concept with KPF was coming up with the structural system for the outside and coming up with a system that works for both office layout towards the bottom half of the tower, and then hotel function at the top of the tower. But so we did a number of studies with KPF and came up with the final number of columns. And these columns are actually not vertical or straight. They're actually bowed in shape to follow the curvature of the tower. And at the corners where you get that notch, those columns are actually curved in two directions. And that's one of the reasons actually we ended up with circular columns. And those columns also split out into Y-shaped columns. And this is the more detailed look at this Y-shaped tower. So just to show the complexity in this area where we have the tower comes up, the column comes up, and then it splits into two elements. And so we did a lot of detailing and analysis in our construction detailing of the project to make sure that things were working properly, as well as the buildability for it. Onto the structural system. So this diagram shows is a good explanation of the structural system. So we have a central core which goes up to the hotel part of the tower, and then that central reinforced concrete core stops, and then we have a steel brace core that continues up in the hotel zone. And then on the outside we have a perimeter frame, which I just showed before with columns. Those columns linked by perimeter beams. And then the central core and the perimeter frame are actually linked together by 4 levels of outriggers. And these outriggers are stationed in the refuge floors of the tower, which is part of the code requirement to have refuge floors. And so, we always position outriggers and belt trusses in the refuge floors because that's a good area for, it doesn't poach onto the leasable floor area. So, it's the ideal place to put them, and it works for the structure. And so we had 5 layers of belt trusses, and then we also used the floor slab and framing to help to tie the internal core and the external frame together, bearing in mind that the external frame is actually curved, so there are these residual axial forces into the floor diaphragm. And for the reinforced concrete core, at the base we had a composite shear core. So what it is we have steel embedded into the core at the base of the tower, and this is actually Arup introduced this first in the World Trade Center project in Beijing, and introducing these plates into the core, because at the base of the tower the core is working very hard. We need the stiffness and we need the strength. So this actually is very beneficial in terms of providing the stiffness, the ductility, and also in reducing the size of the core wall at the base of the tower. I mentioned that there's 4 layers of outriggers. So the outriggers, this plan shows the positioning of the outriggers. So the outriggers are actually positioned to help with the weak direction of the tower. I mentioned before that we've got a slenderness ratio of 8.4. And so in this weak direction, the weak Y direction, we had to use these outriggers to help to provide the stiffness. And the diagrams below show some of the the analysis we did with L.S. Steiner in the construction detailing for how these outriggers then actually get embedded into the core. Another interesting aspect of the structure was that you can see in the tower where we moved from the office to the hotel, there's actually, the tower steps back. And so part of the core disappears. And so, and we also changed, the layout of the core changed to suit the hotel layout. So we had a number of steel elements which are embedded in the core and continue upwards to form the core for the tower. At the same time, we also had transfer trusses. You can see the column line in red. here. There's a transfer truss that runs across here to pick up the face of the tower that continues up for another 80 meters or so. And then onto the design forces. A tower of this type, we would recommend that you do two independent wind tunnel tests to verify the wind loads. And in this case, this was carried out at different stages. And the results you can see on the top right corner actually match quite well. So the wind tunnels were done by BNT and CPP. Also looking at acceleration at the top of the tower, yesterday there was a lot of talk about comfort and also acceleration acceptance at the top of these super high rises. And for this particular tower, we found that from the wind tunnel studies, the results, we find that the accelerations are within international and Chinese code limits, so we didn't have a problem with acceleration. Tower of this type, super high rises, it depends on the location and depends on the structural system, but you find that wind loading dominates in some particular instances and seismic loading in other aspects of the design. This is a comparison for the frequent earthquake and the wind loading in terms of the base shear and the base moment. And we can see that the yellow bar is the wind loading. And then, so we can see that the wind load in the strong axis, the wind load, the strong axis was the y-axis, so the wind load it was actually less than the frequent earthquake. Whereas in the weak axis, where we had a lot of wind hitting the face of the building, then the wind load governed. This is some quick results from the tower analyses. Again, in China, when we do these design, we have to actually carry out two different models, analysis of two different models, to provide comparison and assurance of the design and the answers. And so in this one, for this particular tower, we've used ETAPS and MIDAS. So some other results on the elastic analysis results. One thing that I like to share is with this shear weight ratio consideration. Now, with super high rises, in the code, there's a requirement that the towers need to satisfy a certain shear weight ratio depending on the intensity of seismic loading for the particular site, for the particular building. And we find that this is one of the governing factors in design of super high rises in China, because you have to reach this shear weight ratio. And so it's always a challenge because of your you want to make the tower as efficient and material-wise as efficient as possible. But at the same time, you have to provide sufficient stiffness to achieve this. Another recent code update requirement is on this, we call it the Geo Defense system, whereby there's a requirement that the external frame needs to take a certain amount of shear from in the building. So for our building, we actually designed it to intensity 7. And we were actually, according to the Chinese codes, we were required to satisfy 10%. So the external frame has to take 10% of the shear that comes down the tower. Now, we were finding that this was quite difficult because you would literally have to significantly increase your external frame in order to do this. I mean, I've just shown on the right, there's a number of ways you can do this, to achieve this. In other towers that we've done, the Guangzhou tower, when we were doing Guangzhou IFC, this requirement was not in place, but then Guangzhou IFC actually used diagrids. And so with the bracings, you can get a very strong external frame structure. And for King Key Tower, we had an issue with the weak direction. Again, King Key Tower was a very, very slender tower. and we actually had cross braces, large cross braces to achieve this. Similarly with the Tianjin Golden Tower, the Tianjin 117 tower. For our tower, we didn't, I showed before the structural system where the external structure is these columns wrapping around the tower. So we've got a column movement frame. And so it's harder to achieve that stiffness. And so we ended up with 8%, around 8%. And at the end, this was actually approved through our working through the design and then working with the approval authorities and the expert panel and the experts to get this approved. Just some stories about structural optimization in terms of, in this instance, the tower shape was very strong, and the client and KPF were also very, very strong in this shape. So when we came in, the shape was already quite well determined. And I mentioned before about looking at the external frame and rationalizing the column layout. Well, another important thing was the tower itself is bowed, and if you look at the base of the tower, this is an architectural layout, so it's not quite clear, but the columns actually come down and they actually taper inwards, right? So we actually did a number of sensitivity studies to look at the angle of this taper, and so we with the sensitivity analysis, then we went back to the client, the architect, and also the QS to actually, then the design team together came up with a decision on the amount of bow that was suitable, acceptable. So, so then we came up with a rational and efficient structure, which also the client and the architect were happy with. A similar story that I always like to tell about this one is, this is very much total engineering and architecture. We've got a floor plate. We've got a floor-to-floor height here, and our floor-to-floor height is 4.4 meters. In the design brief, the client asked for a ceiling, clear floor-to-ceiling height of 3 meters, right? And that's what we were all designing to. And we actually achieved this in the steelwork and everything. And then we went away and looked at it and says, let's look at this and let's see what kind of cost savings and what's the issues involved. So we did a number of studies, again, comparing the different floor beam depths with steel weight. And at the end, we came up with, so we had different cases. And at the end, the client and KPF also accepted this where we had slightly deeper beams, but having deeper beams, we actually reduced the amount of steelwork required. So we actually came up with a saving on the floor steel beam tonnage itself. We had a saving of about 10%. This is just on the floor steel floor beam steel tonnage saving by having slightly deeper beams, right? And of course, we didn't achieve the initial wish for 3 meters floor to ceiling height, but then with 2.9 floor to ceiling height, everybody was happy with. Quickly on to nonlinear analysis. So because of the nature of the tower and super high rises, so we carried out, this is part of the approvals process as well, that we need to carry out these nonlinear elastoplastic analyses. And this was done using LS Dyna. Part of the process is we would have specified seismic performance for the tower itself and for the different elements, and the expectation of how they would behave in, say, a level 1 earthquake, which is frequent earthquake, level 2 earthquake, and the rare earthquake. And this was also, this is based on guidance from FEMA 356 and ASC as well. And the results, so the results from the nonlinear analysis pretty much proved the tower does behave to what we've designed to, and then with failure with yielding and failure at the opposite places for good seismic design and good seismic behavior. And as part of the approvals process, experts also asked to do shake table tests So I've got 3 diagrams here. The one on the left is actually in seismic level intensity 7. This was the design for our tower. Now in Chongqing, the design, according to Chinese code, seismic intensity, well, you have to design to seismic intensity 6. But after we had the site-specific seismic studies, from the site-specific seismic studies, it came out that we had to design to the intensity 7. And I think this is also part of the reaction to after what happened with the 2008 earthquake in Sichuan. So we designed the tower to intensity 7, and then with the shake table test, you go and do a table test. So a number of scenarios were taken, and I'll just show you the video for seismic level intensity 8, and you can see how the tower is actually moving quite well, if it works. Okay, maybe not. So oh, okay. Oh, there's no sound. Okay. So there's quite a. Oh. Oops. I missed out a slide, but there's a slide that shows the. So after the shake table test, they went back and looked at in detail the areas in the tower where there's been yielding or failure, and it was pretty much to our predictions in the nonlinear analysis using LS-Dyna. And a quick description of the foundation system. So this is in Chongqing, where we've got pretty good foundation material. So this is on moderately weathered mudstone, and our foundation system uses these hand duct caissons, which is about 4 to 5 meters in diameter, and then they bell out at the base to about 6 to 7 meters diameter. And the caissons vary from about 13 meters to about 25 meters. So that was a quick introduction on the tower. And at the moment, it's under construction. We finished the tower 1 is almost finished, and tower 2 they're commencing construction towards the end of this year. So just show that this is one of the number of towers that we're doing in China, and I like to say that it's been, to me, it's been a very enjoyable process in a couple of years, and we've definitely, in my opinion, we've achieved and exceeded expectations from the client and also from the architect in delivering this world-class tower to them, and the design and the functions. Thank you very much.
Thank you very much, Andrew. Any questions in the room for Andrew? Okay, so then we go. You have a question?
Yes. I have a question, because there is no question in audiences. You talked about the composite wall system. Composite wall system, you insert the steel plates inside the concrete wall. In that case, the kind of the detail complicate the construction. So it could be some delay in construction. So how do you deal with that kind of problem?
Yeah, I mean, there's definitely a trade-off with construction, because the way it is I didn't have a picture there, but it's made up by a number of steel stanchions and also plates that link up, right, to form this composite shear plate in the reinforced core wall. So you do have to erect this first with shear studs on the elements. Then you go and erect the rebar around it, and then you pour. So there is a penalty to time. But I think this is where you have to weigh out all the different issues and the factors, because by doing that, we came down to a wall thickness which was 1.5. And if we weren't, the wall thickness would be around 1.82 meters. So you've gained a lot of floor usable floor space in the design for that. So definitely, if it was a very fast track project, maybe we would go for another solution.
Other questions?
Okay, thank you very much, Andrew. Now